Welcome to Physics Lesson 2.07, Part 2. These are the sample problems for horizontal kinematics. We're going to work through 3 problems, and I'm going to show you some problem-solving strategies for working at your kinematics. So in Part A, we learned about the kinematic equations, and the main ones that we're going to use are V sub F equals V sub O plus AT. That was number 1. Number 2 is x sub f equals x sub o plus v sub o t plus 1/2 a t squared. That's number 2. Number 3 is v sub final squared equals v initial squared plus 2a. This is x sub f minus x sub o. Often it's written as delta x. The 4th one, and we're not going to use it today, is that delta x equals 1/2 v sub o plus v sub f times time. We talked about where this one came from. We talked about where this one came from. I gave you guys this one, and we talked about where this one came from. So when you're working on these problems, what you want to do is you want to start a variable bank, a bank of your variables, to help you pick apart what equations we're going to want to use. And note, I'm going to write this over here in another color. This equation does not have displacement. This equation, number 2, does not have final velocity, although I mentioned you can rewrite this equation with final velocity here and you change that to a negative sign. That will come into play later. Some of your solution sets for the homework, I did this, and you can see that I say this is the equation I used, but we don't use that very often. This equation, number 3, is missing what? There's no time here. And number 4 has no acceleration. So if you have 3 kinematic variables, you can find a 4th using these equations. So to start off with, look at problem 1. You're going to want a variable bank. And the problem reads, the average acceleration of a jet launched from rest off the deck of an aircraft carrier is 40 meters per second squared. Let's talk about that right now. I have meters per second squared, and that's a tip-off. We'll say, well, I'm not sure if I'm looking at acceleration or velocity. Back here it said acceleration, but if you missed that, you should be able to pick it up by the unit, 40 meters per second squared. During a time interval of 1.8 seconds, assume the motion proceeds with constant acceleration. How far does the fighter jet travel along the deck during this time interval? My 5 kinematic variables, and I'm going to actually write them as 6 because I want you guys to get into the habit of writing both your initial displacement point and your final displacement point, but we usually only count displacement as a single kinematic variable. V sub O, V sub F, X sub O, X sub F, A, and T. The other thing we need to do is before we start and for these problems, let me say it doesn't really make a difference, but it's a habit I want you to start getting into, is we want to put the direction of positive. And one of the things I'll do, and this is going to become a really big deal later, is I'll always put the direction of motion in green. So what you're going to see time and again is green represented in motion. Okay, we picked up from our problem that we have an acceleration of 40 meters per second and a time interval of 1.8 seconds. Sorry, 40 meters per second squared, a time of 1.8 seconds. And if I look for the question word, how far does the jet travel? I'm looking for this, and I like to put a question mark next to that because that tells me that's what I'm solving for. We're going to assume our initial, the jet starting from our 0 point. So I have a problem. I need 3 kinematic variables to find a 4th. This doesn't count as a kinematic variable because we're always looking at delta x. We always need delta x. So what am I missing? Well, there was a little nugget of information here. The jet was launched from rest. So that means that my initial velocity was 0. Another thing I like to do is I like to put a little x next to the variable I'm not using. And what I can do is I can use that to see if I'm not looking for v sub f, this is the equation I'm going to want. So the equation that's going to help me solve is x sub f equals x sub o plus v sub ot plus 1/2 a t squared. So when I plug in my variables, this is 0, this is 0, so these terms are just going to go away. And it becomes 1/2 40 1.8 squared. And when I do the algebra, I find out that that is 64.8 meters. All right, sample problem number 1. Let's take a look at sample problem number 2. An automobile with an initial speed of 4.3 meters per second accelerates constantly at the rate of 3 meters per second squared. Find the final speed and displacement after 5 seconds. So they're actually asking me to solve for 2 things. I'm just going to solve for one. I'm going to solve for final speed here in the interest of time. I have an initial speed, so that's going to be my v sub o. I have an accelerates constantly at 3 meters per second squared. And if I wasn't sure, my unit here is meters per second squared. So that tells me that's acceleration, and here's time. So when I get my variables, I got v sub o, v sub f, x sub o, x sub f, a, t. I'm going to assume that this is true for all of these problems, that I'm going to have a positive direction is going to be to the right, and my motion is going to be to the right. So let's bring down my variables. So I have 4.3 meters per second. Here I have an acceleration of 3 meters per second squared. And I have my time is 5 seconds. I am not going to solve for displacement for this problem, so we're going to put x's next to that. But I do want to know what my final velocity is. So if I don't want to worry about displacement, that's going to be this equation. I'm going to use v sub f equals v sub o plus at. V sub f becomes 4.3 plus 3 times 5. And when I solve that, I end up with 19.3 meters per second. Finally, a car accelerates uniformly from rest to a speed of 18 meters per second in 12 seconds. Find the distance. There's my question word or my command. The car travels in this time. So if I write out my variable bank, v sub o, v sub f, x sub o, x sub f, a, and t. I'm going to have a time of 12 seconds. And I'm looking for, I'm going to say I'm starting from 0. I want the distance. So now, where does this 18 meters per second go? Well, I know it's a velocity because it's 18 meters per second. If I read the problem again, it accelerates uniformly from rest to a speed of 18 meters per second. Well, there's that from rest again. So that tells me I'm starting here and I'm going here. Well, wait a minute, what's this accelerates uniformly? And I should have mentioned this earlier. You'll notice, I'm going to grab a highlighter for this. This says accelerates uniformly, accelerates constantly, constant acceleration. Remember, these equations only hold if I have constant acceleration. So when these problems say I'm accelerating uniformly or constantly, that's saying I can use a kinematic equation. So I don't have acceleration in this case, so it doesn't tell me what my acceleration is, and so that's what I'm missing. So if I don't have acceleration, I'm going to have to use this guy here. I lied, I said we weren't using that, and we are. So delta x is going to be x sub f minus x sub o, which, let me write it that way. 1/2 B sub O plus B sub F T. So this is the same thing as delta X. So I know that in my initial X is 0, so I'm just going to say X sub F is 1/2 0 plus 18 times 12. And when I solve that, I'm going to get, I believe, I better double check this one. 108 meters. Well, we didn't get a chance to do a sample problem with this guy, but it would work the same way. So those are your sample problems for kinematic equations. You are now equipped to do the homework for 2.07. So take a crack at that. Thanks for listening and have a good day.